In the last video, we looked at the concept of limits and how it's the idea of finding out what the function value will be as we get closer and closer to a given x value, right? So now in today's video, I want us to look at how we can use the concept of a limit to lead us to the definition of a derivative function, okay? In order to do this, we're going to consider a car's position and time between 2 points A and B in a given route, right? Say we were able to collect this data and this is what we recorded, okay? At position A, we began recording our data and the time was 0 hours and the car was exactly 2 kilometers away from home, okay? And you can see on the spreadsheet here alongside, we recorded the car's position at 0 hours, 1 hour. After 1 hour, the car was 3.47 kilometers away from home. After 2 hours, the car was 5.26 kilometers away from home, right? And then we just collected all this data and eventually the car reached its destination, which was 50.98 kilometers away from home after 7 hours, okay? So now we're going to take this data and we're going to plot it on a Cartesian plane, right? And as you can see, I've already done that, okay? So then we can get rid of this spreadsheet, right? So now we just have our points on a Cartesian plane, right? But in order for us to be able to work with these points, we're going to have to generate a position versus time graph, right? Which is going to roughly map, right, the car's journey, right? And when we do this, we say that we're basically creating sort of like a line of best fit through our points. And what I saw is that the polynomial that can best map the position of this car is the polynomial f of x equals to x squared plus 2, right? And it's just a cubic function, right? And obviously we're considering it only for x values greater than 0, because in this case this polynomial is mapping position versus time. So x is actually t, and right, so f of x represents the car's position over a given period of time t. Okay. So now once we've mapped our car's journey, we now can work with this graph, right, to answer a few questions, right? So when we look at the graph, we can answer questions like, how far away from home was the car after 1 hour and 15 minutes? Okay, that's just simply a matter of going to the graph, okay, and going to 1 hour 15 minutes, so a time of 1 hour 15 minutes, and the graph will tell us or approximate for us that the car was approximately 4.25 kilometers away from home, right? We can also answer questions like, what was the car's average speed when it was 30 kilometers and 18 kilometers away from home, right? So that just means that we need to go to, right, 30 kilometers Okay, so we see over here at point E, the car was 18 kilometers away from home, and here at point F, the car was 26.58 kilometers away from home, but we want exactly 30 kilometers away from home, so we can plot on the graph, right, a position of 30 kilometers, right, and if I just move this, we'll see that we've now gotten a plot on the graph which is exactly 30 kilometers away from home, and that was at approximately the time of 5 hours and 29 minutes. Okay, so we can now work with this point J, right, and this point E, right, to calculate the car's average speed, right? And we know that in order to do that, we say that we just connect the 2 points, right, and the car's average speed between those 2 points is simply just its rate of change, right? So that's just simply calculating the gradient, right? So if we want to know what is the car's average speed, okay, between 18 kilometers and 30 kilometers, right? And well, the average gradient is going to be given by the gradient of the secant line, and we call this a secant line because it's connecting 2 points, right? And this is going to be the secant line JE. Okay, we know how to calculate gradient. It's just a change in y, so the y value at E minus the y value at J divided by the x value at E minus the x value at J. Okay, so this will give us, right, so the y value at E is 18 kilometers minus the y value at J is 30 divided by the x value at E is 4 hours minus the x value at J 5 hours 29 minutes. Okay, so then we can just calculate the car's average speed. So it's 18 minus 30 divided by 4 minus 5.29. Okay, so then this tells us that the car's average speed between the two positions is 9.3 kilometers per hour, right? So this is 9.3 kilometers per hour, right? So notice that this was in kilometers and this was in hours. Okay, so that's basically how we can calculate the car's average speed, and we can do that simply by calculating the gradient between those 2 points, right? However, sometimes you want to answer more sophisticated questions like what if we wanted to know what's the car's speed at exactly 10.25 kilometers, right? So at a time of 3 hours, right, the car was 10.25 kilometers away from home, right? But if I just zoom into this a bit, you'll see that that point, right, is not on our graph, right? So we're going to have to work with an estimated point, right? So if we plot a point that is on the graph at time, still at a time of 3 hours, right, we will get a point K, right, and this point is just overestimating the car's position as 10.98, right? However, it's just how data works in reality. Sometimes you can't get a function that goes through all your data points exactly. Okay, so we're going to work with a approximation, right? But it's just the idea that I'm trying to get across. Okay, right. So if you want to know what the car's speed is at exactly this time of 3 hours, right, what we can do is we can calculate the gradient of secant lines, right, which are getting closer and closer to this time of 3 hours, right? And that's where the concept of limits comes in. So if we wanted to know the car's speed, right, at exactly 3 hours, right, we would have to draw a tangent line, right, to that point K, right? But the problem then is that we can't calculate the gradient of the tangent line because we saw with the previous example, right, that when we calculate gradient we need 2 points, right? And when you have a tangent line, it's just going to go through this single point K, right? But that's where the maths comes in, right? Okay, so what if we started choosing points closer and closer to the time t, right, and calculated the gradient of those secant lines, right? When we do that, right, we can get closer and closer, right, to the car's speed at exactly, right, 3 hours. Okay, so let's choose a point L, right, which is at a position of 12.46 kilometers at a time of 3 hours and 28 minutes. Okay, so we can calculate the gradient of the secant line, LK, right? That's just going to be the change in the y values, so 12 minus 10.98 divided by 3.23 minus 3. Okay, and we get an average speed of 6.43 kilometers per hour. Okay, so 6.43 kilometers per hour. Okay, but then what if we choose a point that's even closer than that? Okay, so say a point M at a position of 11.8 kilometers, right? We can calculate the gradient of that secant line as well. So gradient of MK, change in y value, so 11.82 minus 10.98 divided by 3.13 minus 3. Okay, and we get now an estimated speed of 6.46, right? So 6.46 kilometers per hour, right? But then we choose a point even closer than that. Okay, so there, right? So now we have the gradient of NK, right? So 11.35 minus 10.98 divided by 3.06 minus 3. Okay, and if we round this off to 2 decimal places, we can write it as 17. Okay, so now we have a speed of 6.17 kilometers per hour. Okay, so essentially, okay, what we are doing is we are decreasing our time interval delta t. Okay, so I'm zoomed in like a lot in this diagram at the moment, but essentially what's happening is all of these, right, go down to the x-axis, right, and between, right, the two there's an interval delta t. Okay, so we can use what we've already learned about limits, okay, and we say that we are looking to find a limit, right, as delta t tends to 0. Okay, so we say 10 to 0 because plugging in 0 directly means division by 0, which is obviously undefined. Okay, so we say that the gradient, right, at point K, right, is essentially the instantaneous speed, okay, of the car okay, and this is equals to the limit, right, as we take what do we call time intervals, change in time intervals, which are getting smaller and smaller, but not actually equal to 0, but closer and closer to 0. So we say that we are using the limit language, we are approaching 0 or tending to 0, okay, of the function, right, delta x by delta t. Okay, and you can see that every time, right, this was always kilometers per hour. So essentially this just becomes, right, when it gets a very, 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 very small delta t, it just tends to dx by dt, right? And dx by dt is the rate of change in position of the car at a specific time t, right? And dx by dt, right, is actually the derivative function of x with respect to the variable t, right? So we can actually, using this simulation, right, we can actually calculate the gradient of the tangent line to the point K, okay? Okay, so if I draw a tangent line, okay, to the point K, it's going to appear on screen in a very light blue color, right? But it looks almost like the curve, okay, namely because we are so zoomed into the curve, right? And we see that the limit, right, as delta t tends to 0, okay, for this car, right, at a time of t, right, is equals to the gradient of the tangent line at k. And if you look at the equation of the gradient of the tangent line, okay, over here, you see that its gradient, right, is 5.99, right? So which means that the car's speed, right, at exactly 3 hours was actually 5.99 kilometers per hour, right? And we saw that you can see then above here, when we were taking the gradients of the secant closer and closer to the instantaneous speed at that point k, right, which is essentially a speed of 5.99, which is 6 kilometers per hour. Okay, but we can think of this more generally, right? So essentially what we did today is we investigated what happens when you want to find, right, the instantaneous speed of a car at a specific time, right? And we saw that, well, you can start off with the idea that you can take the average gradient between 2 points, right, and then just move that point, right, closer and closer, right, to the specific time that you are looking for, and you can essentially approximate the speed of the car at that specific point, right? So in general form, what we're saying is that we are looking at some point x, right, and we then take a arbitrary distance away from x, right, so x plus h, right, and each of these points will have a corresponding y value, right, f of x and f of x plus h, right, and if you draw, okay, connect a line between your point of interest x and the point x plus h, right, you have a secant line, right. However, you can then choose, right, secant lines getting closer and closer and closer, right, to your point of interest, which is x, right. Obviously you'll never be able to get exactly on x, right, but you can approximate that, right. But the beauty of maths is that we don't actually need to get exactly to x, right, to the point where our interval is exactly equal to 0. We can just use the language of limits, right, and say that we are tending, right, to an interval difference of 0. Okay, so in this case, when we talk in general form, we are going to be talking about h, right, so this distance away from our point of interest x, we're going to talk about that tending to 0, right. So thus we've now developed our general equation, right, for the gradient of a tangent line, right, and the gradient of a tangent line is exactly the same as them asking you a gradient at a point. Okay, so we can say that what we've done today is that we saw that the gradient of a secant line, right, which is a line going through 2 given points, is just, right, change in y over change in x, right. So it's just our normal change in y over change in x. Okay, and if we make it specific to this, then it's going to be f of x plus h minus f of x, right, divided by x plus h minus x, right. So we have our change in y, right, over a change in x, right, and we can simplify this to f of x plus h minus f of x, right, divided by, well, the x's will cancel out and just simply h. Okay, so that's the gradient of a secant line. Okay, but if we want the gradient of the tangent line, Okay, then we have to take the limit, right, as h tends to 0, right, of the gradient of the secant line, which is f of x plus h minus f of x all divided by h. Okay, and basically all you need to remember is that what that is saying is that we are taking secant lines getting closer and closer, right, to our point of interest of x, and as those secant lines get closer and closer, right, they will eventually become a tangent line at your point of interest x, right, and then that will give you the gradient of that tangent line, right, and this is what we're going to use, right, to calculate the gradient at a point. Okay, and when we do this, right, we are going to say that we are taking the derivative by first principle. Okay, so now there's just 3 key questions that we need to answer. Right, so this is going to be your takeaway from today's video, right? So the first key question is, what is a derivative? Okay, and we've defined this before. A derivative is a function which gives the instantaneous rate of change, right, of our original function with respect to some variable. So the next quick question is going to be, how do you then compute a derivative, right? In other words, how do you calculate the equation of a derivative, right? Well, the derivative function is equal to the gradient of a tangent line at any given point, right? And we already worked out what is the gradient of a tangent line. And we saw in the introduction video that we can represent a derivative as just simply f prime of x, right? So this represents the derivative function, right, and the derivative function, right, is equals to the gradient of a tangent line at any given point, and the gradient of a tangent line is equals to the limit, right, as h tends to 0 of f of x plus h minus f of x all divided by h. Okay, and then now you can answer the question, what is the gradient at a point? Well, the gradient at a point is the gradient of the tangent line at that point, right? If you're looking at some generic curve, right, and you want to know what is the gradient at a specific point A, right, this point is going to have a corresponding y value, f of a, right? You want to know what is the gradient at that point, a f of a, okay? The gradient at that point, right, is the gradient of the tangent line at that point, okay? And we already saw what the gradient of the tangent line is, okay? It's equals to the derivative at that point. Okay. So basically, when you are looking now specifically at a given point, you can see that f prime of a, right, is equals to the limit as h tends to 0 of f of a plus h minus f of x all divided by h. Okay, and that's the 3, right, key questions that we are going to take into our future videos, right? Okay, so this equation over here, f prime of x is equal to the limit as h tends to 0 of f of x plus h minus f of x all divided by h, right? This is the equation that we're going to use, right, when you are asked to take the derivative by first principle, right? They also sometimes say take the derivative using the definition of a derivative. This is the definition of a derivative, okay? And we'll see in the next video exactly how do we use this formula, okay, to compute the derivative from first principle. See you next time. Sleep till